All right, so this is computer graphics number 4. So this will be rotation in 3D. So here's a key point before we go further. Right, in 3D, it doesn't make sense to rotate around a point. Instead, what we need to do is look at rotation around an axis. So instead of rotation about a point, we need to rotate about an axis. And so to give a sense, because if you have sort of a point, you can talk about clockwise and counterclockwise. With an axis, there's no sense of counterclockwise and clockwise. So what we'll do is we'll say that each axis has a direction, and rotation will be by the right-hand rule. So what this means is if I have an axis, like this line right here, with a direction, the rotation will follow the right-hand rule around that axis, like that. And just to be clear, this direction will be given. And then once we give that, we know which way the rotation is going. Now, before we talk about an arbitrary axis, first let's focus on the 3 main axes. So this is the x-axis, the y-axis, and the z-axis. Now, oddly enough, what we'll do first is, actually number things here a little bit, is we'll focus on the z-axis first, and we'll see why in a second. So what's going on in this case is I have our z-axis right there. It has an up direction. We have our other 2 axes, x and y. And the rotation direction will be like this. Now, if you notice, this is the same rotation that we did in 2 dimensions, and z is being left alone, right? So here it's the same as 2D with z left alone. And so, since points in 3D, these have this form, remember we added a 1 to those. To rotate about the z-axis in this case. So we multiply by, we'll define the matrix rz theta. This is by theta radians, obeying the right-hand rule. So all we're going to do is we're going to use the same basic idea. So those will change the x and the y. Those will leave the z alone, and this will leave the final 1 alone. So really nice and easy, right? So for example, to rotate, say, a point like 5, -1, 2 by pi over 3 about the z-axis, just take rz of pi over 3, that matrix above with pi over 3 in it, and multiply it by the point 5, -1, 2, 1. And whatever that turns out to be. Nice and easy. Z is left alone, the 1 is left alone. So, next thing, what we want to look at is the positive x-axis. Before we do though, I want to make a little note here, is this rotation. If you look back at the picture, this is taking the positive x-axis towards the positive y-axis. It's just an observation, just notice it for now. And I'm going to mention it one more time in the next example, and it'll be useful or meaningful or important as we go. So let me clear the screen, and then we'll look at rotation around the x-axis. So 3, rotation about the x-axis. So this is really easy. Graphically, just so we're clear, let's make sure we have a picture, it'll help us. Here's the x-axis. Here are the other 2 axes. We're rotating according to the right-hand rule. We're rotating this way. So notice in this case, the positive y is moving towards the positive z. So what we'll do is we'll have the same matrix, but we'll use a version. We'll switch things around so the x is left alone. So we'll just do Rx of theta. So in our case, it's the x gets left alone. The fourth coordinate gets left alone. And the cosine theta, negative sine theta, cosine theta, those guys in the middle, those do the rotation. So really nice and easy, right? So for example, to rotate 8, 10, 20 by pi over 2 about the x-axis, we simply do Rx of pi over 2 and multiply it by 8, 10, 20, and 1. Nice and easy. Now, last of the principal axes, but by no means the simplest, and we'll see why, is rotation around the y-axis. So this is what's tempting. So before I even draw a picture, right, it's tempting to just do this. Just say like, well, look, let's just leave the y alone, right? Why can we not just do this? And so we sort of could, but there's a problem. So by doing this, what this does is, this takes, because the way we organize it, this takes the positive x-axis towards the positive z-axis. But if we look at our picture, right, so let's actually draw the picture now. So the y-axis goes to the right. The x and the z-axis, those go here. The rotation, according to the right-hand rule, needs to go here, which means consequently that the, sorry, I labeled the z-axis wrong, sloppy of me. But we noticed it because what needs to happen is that the positive z-axis needs to go towards the positive x-axis. So the rotation that we're tempted to do, this goes the wrong way, right? This goes actually sort of the reverse direction. So it's easy to fix because all we do is we negate the thetas and things go the other way around. So to fix these, what we do is we define our r sub y of theta. So if you negate all the thetas, cosine of negative theta is the same as the cosine of theta. The sine of negative theta is the negative sine of theta, so they cancel. So what happens is, and similarly here, now we get a negative sine theta. Ooh, I had a, up in the top matrix I had a 1, or I meant to have a 0 right there. So we get this instead. This will do the job. So, for example, to rotate, say, 208 by pi over 6 about the y-axis, what we do is we take r sub y of pi over 6 and multiply by that by 2081, and that will do the job. Now, last thing then might be like, what about other axes? So for other axes we need to do some shifting first. So let me clear the screen and sort of mention 2 examples, but these can be actually fairly icky. So let's get to those. So 5, other axes. So if they're easy, we can do translations like we did for points, right? So consider the example, let's rotate pi over 6 about the axis x equals 1, y equals 2, pointing up. So just so we're clear, this axis looks kind of like the z-axis, but it's shifted, right? X equals 1 and y equals 2 is here. That axis is this axis, going through that point. So the rotation we want to do is this rotation. So what we'll do is we can take that axis, we can shift the axis to the z-axis, and then rotate and shift back. So we shift our axis to the z-axis, rotate, then shift back. So, in other words, we translate by -1, -2, 0. That does the shift in 3 dimensions. We rotate around the z-axis by pi/6. And then we translate back again. And then to do a point, you just stick a point at the end. So whatever this matrix multiplication turns out to be, let's say for a point like 8, 17, 42, we just put that at the end with our 1, and that does the job. Now, consider this last one, because this is going to get pretty horrendous, and this is actually a complicated thing in computer graphics, is what about rotating about, say, let me draw an axis for you. So the axis I want to rotate around, what if, say, it comes out, for example, from the origin, but it points out at a 45-degree angle in the xz plane. All right, so this axis is a, say, 45 degrees up from x. Right, this is an xz plane. So again, this might be a really ugly picture, so let me draw what might be a better picture. Imagine the xz plane, which is right here. Right, like that. We've got the y-axis sort of pointing to the left and to the right. In that plane, we've got like a 45-degree angle right there. And what we want to do is we want to rotate around that according to the right-hand rule. Like, how would we even do that, right? Let's say by, say, pi/6. So what we need to do here is we need to get that axis to a familiar axis, right? So what we can do in this case, here's our y-axis over here, is we can rotate around the y-axis by pi/4. That will take our axis to the x-axis. So if we do ry pi/4, our blue axis goes to the positive x-axis. So then we do our x pi/6, then rotate back. So in other words, we would do ry pi/4, x pi/6, y negative pi/4. That will do the job. Now, if the axis is more confusing than this could get significantly harder. So if you go into serious computer graphics work, there are other ways to do this. This could be done with quaternions much more easily, differently, but more easily, but sort of more confusingly, because we need to learn about quaternions, and here we're just messing around with matrices. But the idea is we can still do it. It's confusing, but we can do it. So let me stop there. That takes care of our three-dimensional rotations.